Before we begin this journey into space and time, I would like to thank the Science Museum, which is one of my favorite places. I have been coming here for decades. And that simple fact, in itself, tells quite a story. When I was 71 earlier this year, I became the longest known survivor with ALS, a condition that I was diagnosed with in my 20s. Last year, the museum put on a special display to celebrate my 70th. It was a remarkable moment when I came to see it, and hundreds of people sang happy birthday to me. The museum put me in touch again with David Hockney. Hockney had drawn a portrait of me once before, in 1978, when he produced several line drawings. This time he produced an iPad portrait. I'm still not quite sure about the fingers. Throughout my life, I have had a gambling problem. When I was 12, one of my friends bet another friend a bag of sweets that I would never come to anything. I don't know if this bet was ever settled, and if so, which way it was decided. I had 6 or 7 close friends, and we used to have long discussions and arguments about everything, from radio-controlled models to religion. One of the things we talked about was the origin of the universe, and whether it required a god to create it, and set it going. I had heard that light from distant galaxies was shifted towards the red end of the spectrum, and this was supposed to indicate that the universe was expanding. But I was sure there must be some other reason for the red shift. Maybe light got tired, and more red, on its way to us. An essentially unchanging and everlasting universe seemed so much more natural. It was only after the discovery of the cosmic microwave background, about 2 years into my PhD research, that I realized I had been wrong. General relativity predicted that the universe should have a beginning. Up to 1970, my main research interest was in the Big Bang singularity of cosmology, rather than the singularities or black holes that Penrose had shown would occur in collapsing stars. My work on black holes began with the eureka moment, a few days after the birth of my daughter, Lucy. While getting into bed, I realized that I could apply to black holes the causal structure theory I had developed for singularity theorems. In particular, the area of the horizon, the boundary of the black hole, would always increase. When two black holes collide and merge, the area of the final black hole is greater than the sum of the areas of the original holes. This suggested that the area of a black hole was like what is called the entropy in thermodynamics. It would be a measure of how many states a black hole could have on the inside for the same appearance on the outside. But the area couldn't actually be the entropy, because as everyone thought they knew, black holes were completely black and couldn't be in equilibrium with thermal radiation. There was a golden age in which we solved most of the major problems in black hole theory. This was before there was any observational evidence for black holes. In fact, we were so successful with the classical general theory of relativity that I was at a bit of a loose end in 1973 after the publication with George Ellis of our book, The Large-Scale Structure of Spacetime. So the obvious next step would be to combine general relativity, the theory of the very large, with quantum theory, the theory of the very small. I had no background in quantum theory, and the singularity problem seemed too difficult for a frontal assault at that time. So as a warm-up exercise, I considered how particles and fields governed by quantum theory would behave near a black hole. I was expecting that part of an incident wave would be absorbed, and the remainder scattered. But to my great surprise, I found there seemed to be emission from the black hole. At first, I thought this must be a mistake in my calculation. But what persuaded me that it was real was that the emission was exactly what was required to identify the area of the horizon with the entropy of a black hole. The radiation from a black hole will carry away energy, so the black hole will lose mass and shrink. Eventually, it seems the black hole will evaporate completely and disappear. This raised a problem that struck at the heart of physics. My calculation showed that the radiation was exactly thermal and random, as it has to be, if the area of the horizon is to be the entropy of the black hole. So how could the radiation left over carry all the information about what made the black hole? But if information is lost, this is incompatible with quantum mechanics. This paradox had been argued for 30 years, without much progress, which is what often happens in research. But if you get stuck, it's no good getting furious. You just have to keep thinking about the problem while working on something else. Eventually, I found what I think is its resolution. Information is not lost in black holes, but it is not returned in a useful way. It is like burning an encyclopedia. Information is not lost, but it is very hard to read. In fact, Kip Thorne and I had a bet with John Preskill on the information paradox. I gave John a baseball encyclopedia. Maybe I should have just given him the ashes. The fact that I used to think that information was destroyed in black holes was my biggest blunder. Well, at least it was my biggest blunder in science. More recently, I wrote a new book, The Grand Design, with Leonard Mlodinov, to try to address a few issues left unresolved in a brief history. You see, the laws of science describe how the universe behaves, but to understand the universe at the deepest level, we also need to understand why. Why is there something rather than nothing? Why do we exist? Why this particular set of laws, and not some other? I believe the answer to all these questions is M-theory. M-theory is the only unified theory which has all the properties that we think the final theory ought to have. It is not a theory in the usual sense, but it is a whole family of different theories, each of which is a good description of observations only in some range of physical situations. M-theory predicts that a great many universes were created out of nothing. These multiple universes can arise naturally from physical law. Each universe has many possible histories and many possible states at later times, that is, at times like the present, long after their creation. Most of these states will be quite unlike the universe we observe, and quite unsuitable for the existence of any form of life. Only a very few would allow creatures, like us, to exist. Thus our presence selects out from this vast array only those universes that are compatible with our existence. Although we are puny and insignificant on the scale of the cosmos, this makes us in a sense, lords of creation. There is still hope that we see the first evidence for M-theory at the LHC particle accelerator in Geneva. I don't feel the same way about the Higgs boson. Physics would be far more interesting if it had not been found. A few weeks ago, Peter Higgs and Francois Englert shared the Nobel Prize for their work on the boson, and they richly deserved it. Congratulations to them both. But the discovery of the new particle came at a personal cost. I had a bet with Gordon Kane of Michigan University that the Higgs particle wouldn't be found. The Nobel Prize cost me $100. Most recent advances in cosmology have been achieved from space, where there are uninterrupted views of our vast and beautiful universe. But we must also continue to go into space for the future of humanity. I don't think we will survive another 1,000 years without escaping beyond our fragile planet. I therefore want to encourage public interest in space, and I've been getting my training in early. So let me finish by reflecting on the state of the universe. The latest Nobel is another reminder that this is a glorious time to be alive and doing research in theoretical physics. Our picture of the universe has changed a great deal in the last 50 years, and I'm happy if I have made a small contribution. The fact that we humans, who are ourselves mere collections of fundamental particles of nature, have been able to come this close to an understanding of the laws governing us and our universe is a great triumph. I want to share my excitement and enthusiasm about this quest. So remember to look up at the stars and not down at your feet. Try to make sense of what you see and hold on to that childlike wonder about what makes the universe exist. I also hope that the Science Museum's smashing new Collider exhibition will help satisfy our boundless curiosity about our place in the universe. Thank you for listening.